Again, the idea is, well, think about it. Approach 0. And again, the idea is, well, think about it. If you have a finite distance, a to b, and you let the distance of each subinterval go to 0, how many rectangles are you going to have? If you have a finite space and you let the distance between here and here go to 0, you can pack in an infinite number of rectangles, right? If you pack in an infinite number of rectangles, you will have no over or underestimate. It'll basically be like finding the area under a distinct point, which is impossible. You can't do that. But if you say it's really, really, really small, and you can't even put a paper between it, then it'll be exact. And that's the idea. That's the limiting factor. Same, it's kind of basic concept of a derivative, right? Where we take the distance and made it 0, and we're taking the distance and making it 0. Very similar idea. Only now we're talking about an area instead of a slope. How many people understood the idea of this? Good. That's fantastic. More on this in section 4.3 and 4.4. This is all you get for right now. Just a little taste. This is appetizer. Are you satisfied? No, of course you're not. That's why you need more of a meal. This is the meal. Okay? Different method. Antiderivative method.
Practice that line every day.
No, I just made it off the top of my head. Pretty good, huh?
Nice. Improv.
I suppose if that's the appetizer, this is like the salad and the main course, and we tie it all together with the dessert. And then the chapter 5 is icing on the cake, baby. Just how to use it. If you like cake.
Insert your favorite dessert here.
You don't put icing on creme brulee. Burn it. You do, burn it. Anyway, antiderivative method. This I'm going to go a little bit past where the book takes you. The book has you do just what antiderivatives, how to do antiderivatives. What I'm going to do is tell you what an antiderivative stands for and then how to do them. You're going to find out now, I'm going to prove this to you after we do 4.3 and 4.4, so I'm going a little bit beyond. That if a of x, here's kind of the special deal, here's what you find out, the end game of section 4.4 is this basically. If a of x stands for the area under a curve, for some function, if a of x is the area function for some f of x, some curve like this, for f of x, on some interval. I've got to give you an interval, otherwise you can't find an area. Does that make sense? You have to have an interval. Areas are a definite thing. We'll talk about definite intervals later on, but areas are definite. You have to have numbers. Then here's what I'm going to tell you. It's kind of a very cool thing. This is where we're going to end up. Again, I've said it 5 times now. This is where we're going to end up after section 4.3 and 4.4. You get it? We're going to end up with this statement. Which is a fantastically marvelous statement. It's magical right now, because you don't know the concept behind it, but it's magical. What it says is, this thing right here is an area. This thing is an area, right? It says if you take, this is kind of crazy to think about, but if you take the derivative, that stands for derivative, right? If you take the derivative of your area function, it will give you your original function. It will give you the line, the curve. So basically it says this. If your area function represents the area, take a derivative and you get the function back. Does that make sense to you? It shouldn't really, not that much. I'm going to prove this to you later. I'm not proving it yet. What you need to know right now is that if you are given an area function, take a derivative of that thing and it will give you your function back. Well, now that's cool, but we're never going to start with this. We're always going to start with our line, right? That's where we want to get to. So, well, this implies this thing. This says, if we want to find the area under a certain function, we basically need to be able to undo this. We need to undo a derivative. For some interval, let me go through this one time for you so you kind of get the interplay here. Here's what it says. It says the area of a curve is a of x. What I know for sure is if I take the first derivative of the area, that's equivalent to my curve itself. So if I want to find the area under my curve, this statement's true, right? The first derivative of the area is the function. So if I want to find the area of the curve, under the curve, what I'm going to do is undo the derivative that gives me the area. So basically, here's the idea. You pretend that your function is a derivative. If you undo that thing and treat it like a derivative, you're going to find what's called the antiderivative. That is the area under the curve. That's the idea of the antiderivative method. I'm going to get more into it in a second. I'll prove it to you. I'll prove it with an example. I have to prove it to you with 4.3 and 4.4 later on. I'll prove it with a couple examples. So if we're going to find the area under the curve, under f of x, we must undo a prime of x to find a of x, the area. Would you like an example that you can actually kind of see?
Mm-hmm.
I was hoping you'd say that. Have I lost you yet?
No, halfway.
You get this, right?
Yes.
Oh, good, good. Now, this is not what we're talking about today, so
So,
it's good for 4.3. Do you get this? No, you don't yet. Trust me, you don't. You won't get it fully until 4.3 or 4.4. The idea is, can you find an antiderivative? I'm going to teach you that in a second, but I want you to understand the concept behind it as well. The concept is we're trying to find the area under a curve. That's why I gave you this introduction. That's the idea, so I'm trying to get that in your head. Remember how I always kept saying, what's a derivative? What's a derivative? You're like, oh my gosh, slope of period point. You know that, right? Good, because I pounded it in your head, and that's going to do the same thing here. What we're doing is we're finding the area under a curve. That's what an antiderivative is. What I've told you, and I've done it without proof, I'm not going to prove it till later, I've told you this. I said the first derivative of your area is your function. So if I can undo my function by treating it as a derivative, I will find the area function. So basically we need to go backwards from a derivative. Did you get that? If the function is the first derivative of the area, that's what that says, the function is the first derivative of the area, if I can undo the derivative, I get my area. That's the idea. That's the antiderivative method in a nutshell. A very quick statement. Now, let me do some of this with geometry to show you that it does in fact work. Then we'll get on into some antiderivatives and how to do those things. So, example.
Okay, so x plus 1 what do you do? Add 1 to the exponent, so it'd be x squared okay, well when you take a derivative you subtract 1 and then move it out in front. You multiply. for an antiderivative, you'd add 1 to the exponent and then do you divide by 2? Would this be it? Plus C. And then I kind of forget.
If we have a function f of x equals x plus 1, I give you something easy to graph because I'm going to show you the graph in a second. I want us to find the formula for the area on 1 to x. Now, this would kind of be stupid if I give you just 1 to 3 because we could just use the triangle and find the area. But what I want to find is 1 to x, and I'll show you why this works according to that. First
Okay,
off, can you graph this?
he did say he was graphing it.
Geez, I hope so. What's your y-intercept? How much your slope? Would you agree that that is your function? We're trying to find the area of that between, what did I say, -1? Oh, you know what? I want -1. Let's make that negative much more interesting. -1 to x. Now, I don't know where x is. I made it positive, but it doesn't have to be positive. What we're talking about, wherever this x is, is the area of that shaded region. Now, keep in mind that this function is x plus 1. What shape is that? Can you find the area of a triangle?
Yes.
Of course you can, yes. Let's find the area of a triangle. The area, in terms of x, notice I'm using the same terminology I used over here, right? That's an area function. The area in terms of x, wherever x happens to be, is. How do you find the area of a triangle again?
1/2 base times height.
Very good. 1/2 base times height. So I'm going to write 1/2 base height. So that would be 1/2. Oh my gosh, what's the base? Oh, let's think about that. What's the base? Is the base x?
No.
X minus 1. Ooh, close.
-1 plus x plus 1.
How do you find the distance between 2 points?
X plus
Between
1.
2 numbers.
You subtract.
You subtract them. You subtract the numbers, right? You subtract them.
Yes,
So
it'd be X plus 1.
This would be, the distance between here and here is x minus, not 1. This would be, the distance between here and here would be x minus 1, right? There's going to be a difference here. So it'd be x minus -1. Yeah, that's x plus 1. Do you see where we're getting the x plus 1? Well, I mean, you can see it. You can just see it on the graph, really, just intuitively. This distance is x, right? Yes? That's one more unit. That's x plus 1. Not x minus 1. That would be over here. So we have x plus 1. So 1/2, okay, that's x plus 1. Okay. Oh my gosh, what's the height? What's the height?
It would be f of x minus x.
Okay, f of...
X plus 1, x
Not
plus
quite.
h of 1.
No h's. We don't want any h's. You're thinking. I like the thoughts. I like good thinking. You have good thoughts. None of them happen
X
right
minus
now,
f
but that's
x.
okay. All right. Tell me something. If this was a 3, if that was a 3, what would the height be? Very good. If this was a 7, what would the height be? 8.
Oh.
You all see the 8. If this is an x, what is the height? X plus 1. You're taking the number, you're adding 1 to it. That's what the height is. So this height, whatever this x is, right? Doesn't even matter. If it's here, if it's a 1, then it's 1 plus 1 is 2. So this height X plus 1. You okay on the height of x plus 1? The function says the height, right? That's what the function means. So take the value is x, plug it into the function, but plug in x, I just get x plus 1. That's what we do. We don't plug it in and get x squared. That's not what we do. We're not squaring the number and then adding 1. We're just plugging the number in. I said if that's a 3, you get 3 plus 1. If that was a 7, you get 7 plus 1. If that's an x, you get x plus 1, wherever it is plus 1. How many people understand? Raise your hand if you're okay with that. Good. Then our height is also x plus 1. You okay with this so far? I'm just kind of proving this for you with an example. It's not a genuine proof, but I'm showing you that it does work. If I distribute this, I'm going to get, let's see, 1/2. That's x squared plus 2x plus 1. Do you believe me? You should, because that's right. Come on now. If I distribute the 1/2 even further, I get x squared over 2 plus x plus 1/2. You follow me with that so far? Okay. Now here's a cool deal. Would you agree that whatever I tell you for x, you could find the area of that triangle? If I said x is 9, could you find the area of the triangle? Yes, you could. You just plug in 9. This is, in fact, our area function because we made it up geometrically. It's just the base times the height divided by 2. That's all we've done. So far, so good? Now, what I want you to do is do some magic. This is the area function. I want you to take a first derivative of that. Would you do that for me?
It's the original function.
I hope you got magic. Hope so. It's not that great magic. I would have told you it was going to happen. But what's the first derivative of a? And we would denote that a prime, right? That's the first
X
derivative
plus
of a.
1.
What's this? X. Very good, because you bring the 2 down, the 2's simplify, you get x. What's this? What's this?
0.
Aha. Does that look familiar? Yeah, in fact, this is your function. That's true every time. Right? The derivative of your area is going to give you your function every time. That's going to happen. That's just basically one example showing that this is true for this example. Now, it doesn't prove it at length. I will do that later. But it shows you that you can do it. Shall we do one more? Would you like to see one more? Okay. I'm going to kind of start simplifying this a little bit. Okay. You know what x squared looks like, right? Okay, now this is only between 0 and 1, so I'm not going to draw the left side of this. I'm just going to draw that. Jill.
Okay, this was gonna be x cubed over 2. Maybe. No. X cubed over 3? Yeah, I think that's it. Plus c. I'm not sure how to find it on the interval there.
See that that's the area we're talking about right there? Yeah, no? Is that a triangle?
Nope.
Is it an exact triangle?
No.
Okay, so we can't do the same thing, but we're going to use the idea. The idea is, here's the idea. If f of x equals x squared, and f of x also equals the first derivative of our area function, you believe that, right? Then the first derivative of our area function equals x squared. That's a basic substitution. It says if our function is x squared, and we know that a function is equal to the first derivative of its area function. You follow me on that? Then we say, all right, well, if fx is x squared, then x squared equals that. That's our jump there. Can you make the jump? Okay. So basically, we're asking this question. Can you find a function whose derivative is x squared? That's the question you ask. Can you find a function? And you know what we're going to call it? A of x, because that's going to be our area. Can you find a function, a of x, whose derivative is x squared? Let's try a couple. Let's just have some fun and try a couple, right? We know how to take derivatives pretty easily. Let's try one. Let's try, well, if we use some common sense or some critical thinking, I should say, would you agree that you need a power bigger than 2? Probably, because when you take a derivative, that power decreases by 1, right? So let's try x cubed. Does it work? No, because this is going to give you a
3x
prime
squared.
of x equals 3x squared. Right? That's not going to work.
3 in the denominator.
Okay, so we need to get rid of the 3 somehow. So if I can somehow undo the divide by 3, then maybe, oh, let's try that. Let's try x cubed over 3. Would that work? Let's try it. If I take the derivative of that thing, what I would do is I'd bring down the 3, right? The 3 and the over 3 are going to be gone. I'm going to get x squared. Okay. Does that work? Yeah, this one, not so much. No. This one, yes, worked. How many will feel okay with that so far? So you're undoing the derivative. You're going backwards. So is it related to a derivative? Absolutely. But you're going the other way. And we had something unique, right? We had to have this over 3 somehow. Now let me ask you another question. It's going to blow your mind up like a mind grenade. What's the derivative of that? What about 7?
Zero.
Oh. There's another one that works. What about this? Very cool, actually. What about that? Any constant. No matter what it is, any constant is going to go away when you take a derivative, right? So what you actually get here is a family of curves. Each of which would work as an area function. So here's what we've done. We've started with this function and we've said, okay, I know the function is actually a first derivative of an area function, whatever that happens to be. So I'm going to set my first derivative of an area function equal to it. I'm going to undo that, treating it like a derivative and undoing a derivative. That's why we call it the antiderivative method. Okay, you're undoing anti, it's opposite of derivative, means derivative, so You're undoing a derivative. That's what we're doing here. Now, unfortunately for us, this is a situation, right? We have we have an infinite number of possibilities for the area function that it could actually be. And in general, that's what you have to put. You have to put that sum of your zone out. You have to put that plus c. The plus c is important. It represents a family of curves, each of which could be the area function. Now, I've also said some specific things about this. I said between 0 and 1, which is going to help us out a little bit, but if I didn't say that, this would be the general area functions of x squared. That's what it would be. You'd have to have more specific information in order to give me an actual verified area. Do you follow me on that? You have to have that. So, do you mind if I go over here? Do you have any questions about this one? Are you with me so far? That there's more than just one of them right now?
Who's the first for you? You actually asked before racing.
Say what?
You actually asked before racing.
I know, right? I was polite today. Oops. So a of x equals 1/3 or x cubed over 3 plus c. C is a constant. C is also the y-intercept of a of x. If something's the y-intercept of a function, you should be able to find it by plugging in 0. True? So what this means is that a of 0, if I plug in x equals 0, can you verify that that's going to give me just the c? 0 cubed over 3 is 0 plus c, so it's going to give me c. Now, I don't want to blow your mind up too much, but for this context, do you understand that this area curve is from 0 to x, wherever x is in this case? That's what that stands for. So this interval that interval is 0 to x. This one might throw you for a loop, but I need you to stick with me, okay? If this is the area from 0 to x, do you follow me on that? It's from 0 to x. And we are finding the area from 0 to, what do we plug in for x?
1.
No, we didn't plug in 1. To find this, what do you plug in?
0.
You plug in 0. When you plugged in 0, what's the area from 0 to 0? What's the area?
Doesn't
It's basically
exist.
saying, what's the area of a single point? Can you find the area of a single point? A point is that which has no breadth. So that means you have no width there. So you can't find an area. It's 0 times whatever the height is, but you still get 0. So I know this is kind of awkward to think about the area of a single point, but that's what you're doing here. You're saying, all right, I'm going from 0 to, I plugged in x equals 0. That's how I got this. That's 0. So what this says is, this is basically the area of a single point. When you set x equals 0, your interval is from 0 to 0. That's the area under a single point. The area under a single point is always 0. If you took any statistics at all, you know this, with continuous distributions. If you ask what's the probability of an exact number, it's always 0. You can't get it because there's an infinite number of possibilities. That's the same idea. The area is 0. So when you set x equals 0, the interval is 0 to 0. That is the area under a single point. and that's 0. So what this says is, from here, here's what this says. It's 2 parts. Oh, I gotta sneeze. Oh, it didn't come out. Oh, don't you hate that? Were you all ready for it and then nothing? Oh, I hate that.
And then your nose tickles like.
Yeah, I hate it. Nose tickles. Oh, bummer.
It actually looked like you sneezed for a second.
I tried. I kind of pretended, just so it would look good on camera.
Valiant effort.
Thanks. So, here's what this part says. This says if you're going to plug in 0, your area goes from 0 to 0. That's area
So
under
C
single
is
point. That is
0.
0. This part says,
When x
well,
equals
I
0.
know when I plug in 0 to my function, I get C.
Oh, but it's a
Therefore,
constant, so it's
if
always
A of
0.
0 equals 0 and A of 0 equals C, how much does C equal?
Yeah, so.
Yeah, that's right. What that says is, though, even though we had the C, we had to take care of the C. The C doesn't always have to be 0. It can be numbers, too. We're talking about initial value problems later on, later on in this section. You might have some C's that are numbers. In this one, you get a 0. So this is what you'd be able to do from this part. After you find your C, you go, okay. Then the area of that curve is x cubed over 3. Now you can start plugging numbers in. Now that you've done with the C. On the interval of 0 to 1, the area is, well, let's fill that in. Our area went from 0 to x. Can you tell me what is the x value of our interval there, where we're stopping? You can now plug that in. Now that you don't have that c, you know the c is 0, right? You'd be able to plug in the x of 1. You go, okay, well, then the area that stops at 1 is 1 cubed over 3. Or 1/3 square units. Now that's our idea. Did you follow the idea? I've given it to you in terms of geometry right now. I've showed you some interesting ideas with area to kind of flesh this thing out a little bit. Right now we're going to take a jump away from the actual area. I just wanted to introduce it to you. So it was a very long introduction. Do you understand the introduction? How many people do feel okay with it? So rectangular method is you cut it into rectangles. We'll talk about that later. Antiderivative method is you go, okay, the first derivative of the area is my function. Let's undo a derivative. That gives us an antiderivative. We somehow have to mess around with the c. We have to figure out what c's are. I'll show you better ways to do this as we go on, by the way.
Okay.
Better ways. Yeah, I need you to understand the idea. You need to get the idea. I'll show you some shortcuts and ways to work around that. You follow? But you have to understand the idea. Now we're going to practice most of the rest of our time in this section on how to actually do the antiderivatives. This was fun, but I haven't showed you any techniques on how to do that yet. I've said basically you need to be able to undo it, and we kind of guessed and checked over here. Would you like some better ways to do this?
Yes.
Absolutely. So we're going to start talking about that. This is called the indefinite integral. Indefinite means that I'm not going to give you boundaries yet. I'm not going to give you 0 to 1 yet. That would be a definite integral. That would be the area between the points. That's what we were able to find, right? An actual number. What I'm going to leave you with is how to get down to here, that part. This would be indefinite. Is say you have a plus c, you don't know where you're stopping, you don't know where you're starting. It's just an indefinite integral because I haven't given you a range of numbers. Therefore, you can't find the definite area. We're just having the function of the area. Do you see the difference there? If you didn't catch what I said, rewind that and repeat that. Some of you get kind of like weird looks. You don't quite get that. I'm going to just leave you here. I'm not going to give you numbers to start and stop at. I'm going to leave you here, show you how to get this. And later on, we'll talk about how to do the whole thing together. So remember, this was an introduction. So indefinite integral means that you're not going to be able to find the area definitely. That's why we call it indefinite. Oh yeah, I guess I should call it, this will be like a subsection. So there's a new word on the board, integral. I'll bring down to what an integral actually is. It's not a hard concept. Given a function, let's call it f. On some interval, let's call it I. I know this doesn't start out so fun right now. Okay, it sounds boring. It's not that bad. Just stick with me. Given a function f on some interval I, capital F is called the antiderivative. Please make a note here. This is also the area function. Okay. In general, we call the antiderivative just the capital letter of whatever the function is. So if we have a function f, the antiderivative is capital F. That's all we're saying here. It will stand ultimately for the area function of your curve. Do you follow me on that? That's what it'll stand for. F is called an antiderivative. If this is true. If you can take the first derivative of your capital F, your antiderivative, and it equals your f of x. You'll notice I used the word and instead of the word the. Think back to like 10 seconds ago, maybe like 30 seconds ago, when I said you had a plus c. You can actually almost see it in the purple writing that it doesn't quite erase that well. Remember how we had several, actually an infinite number of functions that you could take a derivative of, and it will give you your original function back again? That's why I say and. That plus c gives you a whole bunch of them, a whole lot of them. And so what we're doing here is we're saying f. F should be some function that when I take a derivative of it, it gives me my function I'm looking at. That's what happens. That's what an antiderivative is known as. Now, we just talked about it like this. Right? Same stuff. A was the antiderivative. F is the antiderivative. Same stuff. Okay? Let me give you the example that we just talked about.
So capital F of x is the same as A of x. So we're saying same as area.
You remember this example, right? In fact, it was on the board. It's on the board right there. Here's what we'd say for this. We would say that f of x has an antiderivative of capital F of x, and capital F of x should be 1/3 or x cubed over 3. You okay with this so far? Is this the antiderivative or an antiderivative?
It's one of them.
It's one of many. It's one of many. This is an antiderivative. This is one antiderivative. I'm going to say anti-d. Why is it antiderivative? Why? Well, look at, if you take a derivative of this, does it not equal this? Why? Because the derivative with respect to x of this thing is this thing, which is f of x. That's why it works. This is all I'm saying here, folks. An antiderivative is this property. It says I take a derivative of it and it gives me a function. That's what it is. This is one of those. Are there more? There are many more. There are infinitely many more. I'll give you another one. Another f of x would be x cubed over 3 minus 4. Is that another one? That's another one of those antiderivatives. That's why, in general, all of them will have this form. That's why we have the plus c, to say, okay, you know what? I'm kind of tired of writing every constant over here. I don't want to write minus 4. I don't want to write plus 3. I don't want to write plus whatever. I don't want to have 0 plus pi minus 1/2. That's all garbage. I don't want to write that. I want to represent this. This represents all of the possible antiderivatives. Do you follow me on that? I can't have any other x's because that would alter the derivative. But constants don't, because when you take a derivative of a constant, it gives you 0. So this right here is all antiderivatives, the family of all antiderivatives.
And then there's also the integral.
I'll talk about that next time. This represents the family of all possible antiderivatives for f of x equals x squared. All possible antiderivatives will other functions have different antiderivatives? Of course they will. Of course they will. Other functions have different derivatives, so they will have other antiderivatives. What I will do next time is I will talk to you about what an integral is, what integration is. It's basically you find out the same thing as doing antiderivative. So I'll show you some notation that will be where we continue. Our study of calculus has brought us to this point where we're not talking about derivatives so much anymore. In fact, we're basically doing the opposite of a derivative. From last time, we learned that if a function has an area under its curve, that's the area function, or in other words, that's the antiderivative. So basically, it's left to us to undo a function by pretending it's a derivative and saying, how can I reverse the process of taking a derivative? That process is called antidifferentiation, or finding the antiderivative. We left with this example. The antiderivative of x squared is 1/3 x cubed plus c. Why the plus c?
Because any constant.
Good. Yeah, the point of an antiderivative was if I take a derivative of it, in other words, the derivative of 1/3 x cubed plus c, it will give me back my original function. That's the idea of an antiderivative. I take a derivative of it, it gives me my original function back. Does that make sense to you? The plus c is there because, well, any constant's going to go away when I take a derivative. So that is basically a family of curves, a family of area curves for which when I take a derivative of it, it gives me my original function back. Did you understand that from last time? That's basically a last time concept. Now, the process of finding the antiderivative is also known as integration. So when you hear the word integration or find the integral, it means find the antiderivative. Does that make sense to you? So antiderivative and integral, or antidifferentiation and integration, synonymous. They mean the same thing. This process, and I mean the process of finding the antiderivative, is also called integration. Let me show you something. Here's what basically our definition in a nutshell. This is really it. Our definition of an antiderivative in a nutshell says, if I take the derivative, I even have it on the board already. If I take the derivative of my antiderivative, it gives me back my original function. Do you follow that? If I take the derivative of this thing, it must give me this thing. Do you follow? Okay. There's another way that we're going to write this. You see, this is kind of confusing because this doesn't let us go from here to here, right? This basically just says, if I do this thing, it will give me this thing. You follow? So we're going to write this a little bit differently. We're going to introduce a symbol called the integral. Remember, an integral means find the antiderivative, or perform integration, which is to find the antiderivative. So this and what I'm about to write mean exactly the same thing. This says if I take a derivative of the antiderivative, it gives my function. This says if I find the integral of my function, it will give me my antiderivative. Plus c. Because we don't know the constant, right? We talked about that already. It's a family of curves. By the way, is that C important, that constant? Yeah, that's 2 points on the test, right, every time. So you have to have the C. That represents, I don't know the exact integral as far as the constant, and it represents a family of curves for which I take a derivative and I get back my original. So this constant must be there. And this right here is called your indefinite integral. I think I referenced that before. I said it's indefinite, an indefinite integral, because you don't have any boundaries. You don't know where you're going. Basically, right now, all we're doing is finding the area function. It's very similar to this. You remember when I had to find derivatives? You ended with things in terms of x, right? So while that represented a slope, it wasn't an actual slope until you plug a number in. You follow me? This is the same thing. This is going to represent an area, but it's not an actual area until you plug something into it. And that's why it's called indefinite and not definite. Definite would be I'm able to plug numbers in and I get areas out. This is called the indefinite integral. The indefinite integral. And these things say exactly the same thing. Interchangeable. This one says take a derivative of your antiderivative, you get the function. This says find the integral of your function. What this says is this. It says find the antiderivative of this. Ah, there it is. That's the whole idea. Do you understand the notation we will do?
Why is the dx there?
That's a good question. I'll get to that in just a second. That dx tells you what you're taking the integral with respect to. So what your variable has to be. So this dx right here says I'm taking this with respect to x. So that variable has to be x. If it's not, we can't do it. Does that make sense? It's got to be there. And we'll talk about this a little bit more as we go on and on. But basically, I want to get down to the names, the notation. What's that called? That's integral symbol, or integral, that's right. What this means is find the antiderivative, or undo this as if it were a derivative of something. So give me some function that I can take a derivative of, and it will give me back what you start with. That's the whole idea right here. You okay with this so far? One note, this is also true. Oh, this doesn't blow your mind, but I'm basically restating things a few different ways so that you see them a couple ways. Let's see if you can manage to do this. This is kind of critical thinking on a lower level. What's that stand for? Integral, or what else was it called?
Antiderivative.
That's an antiderivative, right? What would you suppose would happen if I took a derivative of the antiderivative? What do you think it's going to give me?
Original function.
Basic function.
The f of x. This is true. That's a true statement as well. That dx, I'll make the note right here. That dx tells you what variable we are integrating with respect to. So this right here says which variable to integrate. For instance, that's why when we did this, now we can actually have symbols for it. Let's go ahead and try to do an example that we had like probably 5 times, but just so you get the symbols down. We've actually done this problem. I think we've done it, I've had it on the board several times, but we've actually done it twice. The integral of x squared dx says, I want you to find the antiderivative of this function. What's the function?
X squared.
With respect to the variable x. That should match up. That has to match up for you to do it, okay? You can't do it if it doesn't. At least not with
Third time
our
it
single
uses
variable
example.
calculus that we're doing.
On
So
all
if
of
we're
it.
doing the integral of x squared dx, we're going to find the antiderivative of x squared. What's the antiderivative of x squared? You actually already have that. Yeah, that's the 1/3. Or x cubed over 3 is fine. That doesn't quite do it yet. We also have to have, it's crucial, we've got to have that.
Plus C.
Oh, minus C, right? And also minus C.
Well, if you had minus c, you could write that as plus negative c, right? So you're always going to write plus c. So c is just some arbitrary constant that can stand for anything. That's how you do most of these problems right now. You kind of find, it says antiderivative of this function with respect to that variable, and we know how to do at least one of them, right? But we don't know how to do any other ones. So right now what I'm going to do, I'm going to give you the basic integration table. Listen, if it doesn't fit in the basic integration table, you cannot do it right now. Okay? You can't create your own calculus here. If you do, you're better than Isaac Newton or Gottfried Leibniz, who invented this stuff way back in the day. That day was 1600s, so probably not going to happen. So don't invent this. Just follow the table. You do have to memorize it. I'm not going to put this on the board, but trust me, you will. The only tough ones are really the some of the trig ones that I'm going to give you right now. Some of the trig integrals are hard to memorize. But think of it this way. You already know the derivatives, right? We're just undoing them. So that's where all this stuff's going to come from. In fact, the table I'm about to give you is going to have the derivative and then the integral that's associated with it. You ready for it? Okay, so.
And this is called integration table?
Yeah, basic integration table.
I'm afraid to see what the advanced integration table would look like.
You know, there's a lot of them. There's a lot of integration tables.
What is that?
Yeah, most of the back of your book has just all those weird pages, right? That look at, what are all those, the curvy things? Someone had fun just scribbling. No, no, no. Those are integrals, and they mean something, right? They all have different formulas. By the way, this long, what is that thing? It's integral, but what does it look like? What letter?
S.
It's an S, and what we're going to come across in section 4.3 is that that's actually a sum. This is going to blow your mind. But remember how I told you that you can add all the rectangles together?
Some of the rectangle.
That's what you're doing. It's a sum. It's a sum. Sum with a limit, basically. That's where the dx comes from. I'll show you all this. I'll make it very clear to you as we get there, but this is what we're doing. This is a way that you're adding all the infinite rectangles together and getting an area. You get it? Kind of cool. Kind of cool. It all makes sense in a little while. So basic integration table. Like I said, I'm going to start you off with the derivatives, and we're going to come up with the integrals that are corollaries of them. Because we know an integral undoes a derivative, right? So if we know the derivative, we should be able to somehow manage to get an integral out of that. So let me ask you this. What's the derivative? We'll start very simply. What's the derivative of x with respect to x?
1.
Very good. 1. Derivative of x is simply 1. Derivative of 2x would be 2. 4x would be 4. So the derivative of x is 1. What that means is this. Hopefully you find out what I'm going to do here. What's the integral of 1? What do you think? If the
X plus
derivative
C.
of x is 1, the integral has to undo a derivative. That's what this says here. A derivative undoes an integral undoes a derivative. So they have to go in
Where's
reverse.
plus C?
They're like inverse operations like division, multiplication, addition, subtraction, square and square root. Same idea. So if the derivative of x is 1, the integral of 1 is x. Sure. Why? Think about it. You're undoing this like it's a derivative, right? That means if you take a derivative of this thing, it should give you back that, does it? No, we're missing something here.
There's a plus.
Plus C. You okay with this so far? Okay. You know, let's do this in general. What was the derivative of x to the r power? What do you do with that? What do you do?